conference. And my name is Wendell Lee. I'm from Dassault Systems Simula Corp, the Power Flow team. The topic of my presentation is a hybrid lattice Boltzmann approach for simulation of high-speed flows. And some ideas behind the hybrid lattice LB approach is different lattice has different characteristics. For the standard lattice widely used, the D3Q19, it is computationally efficient. It has a low numerical dissipation, but it is limited to the subsonic flows and with low Mach numbers, and it is also constrained by a lack of isotropy. So in power flows, transonic flow simulation, we use a D3Q39 lattice. And in the literature, there are different kinds of D3Q39 lattice. They differ in stencils and weights. And in power flow, we use this kind of D3Q39 lattice. And in this lattice, it is capable of simulation of thermal high speed and compressible flows when coupled with additional numerical scheme for energy conservation. And it is astronomically more sufficient as demonstrated by other researchers, but it's significantly more computationally expensive, and it also suffers from high numerical dissipation. So considering their respective advantages and limitations, we want to deploy the D3Q39 lattice only in specific domains in transonic flows, and deploy the D3Q19 lattice in the rest of the simulation domain containing simple and subsonic flows. Actually, this ideas has been introduced. There are some research efforts in these ideas. For example, in the last year's DSFD conference, Dr. Konis, I think he introduced a similar idea in the semi-Lagrangian framework. And in this presentation, we will introduce this. We will implement this idea in the power flows double-sided servo technology. And first, my colleague Junyo Wang will introduce the hybrid lattice approach in the power flow framework, and then following by that, I will introduce the validation cases. Actually, we have tested a lot of cases. These four are typical cases I want to present. And now I want to welcome my colleague Junyo Wang to introduce this interfacing algorithm. Hi, Junyo Wang, can you speak? Maybe you are muted.
Yes.
Okay.
Okay, please.
My colleague Junyo Wang, can you hear me?
Yes. I think.
Yeah, I think he's online, but can you give him a?
Who is the name, please?
It's attendee here. This one. Let me. Maybe I can log in to talk. Can you talk?
Yes.
Yes.
Okay, good. Yeah.
Yeah. Thank you. And so I will briefly introduce the algorithm we use for interfacing between different LBM domains. So we use several pair-based algorithm to connect the subsonic and transonic flow domains. So on the right-hand side, there's a picture. You can see that there's a subsonic lattice on the left and a transonic lattice on the left. And on the interface, there's several pairs to connect the left domain and the right domain. So a several pair consists of two servos, the left servo and the right servo. For illustration purpose, you can see two servos here, but in reality, they coincide with each other. So the left servo only interacts with the voxels on the left domain, the subsonic domain, and the right servo only interacts with the voxels on the right domain. And the information can pass through the servo interface so that we can ensure the mass and momentum conservations through the servo. And on the surface pair, we do the average of the macroscopic variables like density, momentum, and the temperature, so that we can ensure smooth flow transition, and also again the mass and momentum conservations. So this is implemented based on the power flow. And for more details, I would suggest to have a look at the reference list on the slides. So it's similar to our numerical schemes for the sliding mesh technique. Yeah.
Okay, thank you. Yeah, I will go ahead to look at the validation cases. If you have more questions in the implementation of this algorithm, we can discuss in the questions section. The first case I've introduced is also the salt shock tube. And this is 1 meter, the length of this tube is 1, and at the 0.5, there's a diaphragm. At time start from 0, the diaphragm will broke. So there are 2 waves generated. The first is a shock wave propagating to the right, and another wave is a rarefaction wave propagating to the left. And this is, we will capture the transient state at this time to see these 2 waves, and this is our case setup 100, 1000, and 4 to represent the 1D Riemann problem. And we select a relatively new low relaxation time to reduce the vicious effect. And we selected 3 different kind of lattices: pure Q19 lattice, and pure Q39 lattice, and hybrid lattice. Between this 0.76 and 0.9. We want to put this here because there's a shock transition to here. So we will see if there are any loss after transit, after the shock wave transit through this interface. And this is the result for the normalized profiles. This is from the pressure, we can see the rarefaction wave will propagate to the left, and this shock wave to the right. This is a hybrid interface. We can observe that the hybrid IBM approach allows the path of the wave to the interface without observable loss. And from this T, we can see that in the Q19 regions, in the for the pure Q19 or in the hybrid 19, we can see that the profile basically maintains the Q19 profile, the green one and the red one. And if we use a pure Q39 region, lattice in this region, there are some slightly rounded result. And the next validation case is a transformative flow around the sphere. This is a DNS case with a high Mach number and relatively low Reynolds number from 50 to 300. By adjusting the viscosity, we capture this with the same velocity. And previously, this is a high Mach number problem, so we can only use the power flows D3Q39 lattice to avoid the Mach cap and the instability when using the D3Q90 lattice, because the Mach number is about 1. The maximum Mach number about 1.60. And we focus on the drag force on the sphere. This sphere has a diameter of 0.1 meters, and this is a simulation volume 100D and 80D, and in the direction perpendicular to the screen, this is 80D, and we use the inlet velocity according to the Mach number, and the sphere is a no-slip wall. And we use a cylindrical shape as a D3Q19, D3Q39 region. This is not a box, this is a cylinder. This is a diameter. And we also investigate other arbitrary shapes for this D3Q39 region. And this is a visualization of the, this is a visualization of the Mach number in the flow field. Basically, this is a pure Q39 lattice, and in the cylindrical, in the right figure, we can see, we will see the Q39 lattice in this region. We can't see any difference in the flow field Mach number for the pure Q39 lattice and the hybrid lattice. And this is drag force. Also, we can see this is a pure Q39 lattice in the cross, and in the circle it is hybrid lattice results. Basically, there's no observable difference between the pure Q39 lattice and the hybrid lattice for the flow field and the drag. And then we investigated different hybrid region shapes. And these three Q39 regions are from the Mach number isosurface of 0.86 for different donut shapes. Because there's different random numbers, the shapes are a little bit different. Still, we can't see the big difference. Either we use a cylindrical transonic region, or we use some other arbitrary shapes. So the observation is that hybrid IBM approach is robust, and as long as the critical flow regions or the high Mach number regions is covered, the simulation result will not be affected. And the third validation case is a M6 wing case. This case is a classical transonic flow case to test the CMD solver. And there are some complexities in the transonic flow, such as local supersonic flow, shocks, and the turbulence boundary layer separation, and the wingtip vortex. And in this case setup, we this free stream Mach number is 0.84. There's a angle attack about 3 degrees, and there's a Reynolds number. And we compare with this case for the hybrid lattice solver using the isothermal of Mach number 0.86. About in this region, the Mach number is about 0.86, and we compare with the pure D3Q39 lattice approach. This is a visualization of the CP distribution on the top of the wing. Basically, we can't see observable difference. There's both of them has a lambda shock. This is a two shock meet at this point about 0.84. And both of them basically we can see there's an invisible difference. And for the CP distributions along this wing, basically we can see the result are the same. So the observation is the D3Q39 lattice is used only in this region, but the results are basically the same as using the pure D3Q39 lattice in the whole simulation domain. So this hybrid approach has potential to save the computational cost. And the final validation case is a 3D monopole acoustic case. Is in the free space or in the near a wall. And this monopole will vibrate at 1,000 Hertz frequency, and it is located as 2 lambda. And the source has a diameter of lambda over 8. And there are some receivers in the circle about 3 lambda. We implement the pressure and the velocity on the surface of the source. And there are some free stream, there are some analytic solutions in the free space and in the plane diffraction. In this, the analytic solution is from the solution of the wave equation. And this analytic solution, it just assume that another monopole here. And from the pressure field of the I want to introduce the hybrid interface is around here. And this is pressure field. We can see from the pressure field that the D3Q39 lattice has more dissipative features compared with the hybrid, because most of the regions are the Q19 regions. And from the monopole directivity, we can see that the hybrid lattice matches better with analytical solution. And if we put several probes here to see the decay of the PRMS values, because this is just the 1 over R in the, if we far from the monopole, the pressure will decay. We can see also the hybrid lattice matches better with analytical decay. And the observation for this case, the flow in the D3Q19 lattice is more dissipative than in the D3Q39 lattice, and the hybrid approach can take advantage of the low dissipation nature in the D3Q19 region. And if we put a plane here, we can observe the same phenomenon. There's more dissipative in this lattice, and the hybrid one will match better with the analytical result. And so the conclusion is the hybrid lattice can preserve the flow dissipation property of the D3Q19 region while maintaining the aerodynamic accuracy for the high-speed regions. So our observation is the new double-sided surface-based hybrid lattice approach is stable and robust. It is a powerful feature to specify this D3Q39 region with arbitrary shapes. And this hybrid RBM allows accurate prediction of shocks, demonstrate a great precision to save computational cost, and preserve the low numerical dissipation for acoustic problems, and able to predict accurate aerodynamic performance for high-speed flow applications. And in future work, we will extend this application of this hybrid approach to a broader industrial CFD domains such as airframe and jet noise, other applications. So,
okay.
Yeah.
Thank you. Thank you too. Thank you also to Professor Wang for the clarifications. We have two short questions. Okay, the first is regarding the energy part. Do you also switch from entropy to total energy equation in the subsonic and supersonic parts respectively?
Yeah, I can answer the question. So actually, for both the subsonic and supersonic domains, we use total energy without the total energy equation. So that is, there's no entropy here. Like we all use total energy.
Okay.
Yeah.
Okay. The second question. Is there a paper or patent discussing the coupling Q19, Q39 in detail?
Yeah, I think I suppose there can be a conference paper just in this conference. I don't know. I think there's a conference journal, right? I'm not sure if there's a conference.
Yeah, there is a conference paper about it, but there is no detail regarding the coupling.
Okay.
That's why I was asking.
I mean, yeah, for this conference,
Okay.
should we can submit an abstract to this conference? If we can, we may provide more details for this coupling.
Okay, thank you very much.
Yeah.
Okay. There are other two questions. We try to be on time. Can you show me some theoretical evidence why the dissipation of D3V39 lattice is higher than D3Q19?
Yeah, the dissipation of the D3Q39 has more dissipation. We observed in several cases, and this is made due to if in the transformative flows, we may introduce some artificial viscosities in this D3Q39 lattice to increase its stability. So this artificial viscosity will first introduce more dissipation. And there are other sources. For example, if we use a fractional lattice Boltzmann method, fractional steps, note the step with displacement of 1. So the fractional step will also introduce with dissipation. And I think this has been discussed in a paper, and they may other sources to introduce the dissipation for the D3Q39 lattice itself. But currently I'm not sure for that part.
Last question. Short, what boundary condition are used?
You mean at the interface, or which case?
I don't know, probably.
He may
the solid boundary.
Okay, the solid boundary. For example, this
the acoustic case, I think.
oh, okay. The solid boundary is pressure and the velocity around it, just the pressure and the velocity according to this equation. There's no other boundary. Yeah. And the other boundaries are the outlet, free stream pressure and the pressure.
Okay. Okay. Thank you.
Yes, thank you.
And we can move to the next speaker, which is Dominic Wild. I give you the permission. Okay. Okay, so now you can able to share your screen. The title
could work right now, right?
Yes.
Okay, perfect.
The title is Exploration of Three-Dimensional Compressible Flows by the Semi-Lagrangian Lattice Boltzmann method. Please, thank you.
Yes, thank you. My name is Dominic. I'm from the University of Siegen and the Bonn-Rhein-Sieg University of Applied Sciences. And today's talk is about the semi-Lagrangian method, about which we heard some stuff before about the method. More pond, we are operating in a static reference frame, which means that we don't shift velocities during our streaming step. And I'd like to say some words about the compressible model before I go to the velocity sets, which is the main focus of this talk, before I present the results which we gained with complex three-dimensional flows, which I will show later. So we are operating in cells, and the cells have support points which are not equidistant, which is why we are able to use high-order polynomials in space, which also renders our solution high-order in space. And concerning the equilibrium, we use a fourth-order Hamid polynomial equilibrium. And to gain a variable adiabatic exponent, we have a second distribution function, which is then coupled with our energy moment. And we use a quasi-equilibrium for a variable Prandtl number. So the streaming step is, and you could, perhaps you know this slide because I showed it several times. In principle, we can go in this during the streaming step over multiple cells to identify the departure point and then apply an interpolation within the cell where the departure point is located. And this is the interpolated point, which is then streamed to the desired point, starting point. And the advantages of the semi-Lagrangian streaming step are basically that you can apply larger time step sizes compared to Eulerian schemes. It features high order solutions, and we are able to apply special off-lattice velocity sets. And the main focus of this talk is the quest for 3 dimensions, because it was not quite clear in the beginning how we can go for 3 dimensions efficiently. And normally, if you have a 1-dimensional quadrature rule, like this 1D Gauss-Hamid quadrature, then it's constructed by the roots of the 3rd-order Hamid polynomial, right? And to go to 3 dimensions, or to 2 or 3 dimensions, you normally apply the Gauss product rule, which is nothing but a tensor multiplication. So this turns your D1Q3 into a D2Q9 and D3Q27 lattice, which is the standard for weakly compressible flows. But for fully compressible flows, we normally have to apply a 5th-order Hamid polynomial, which is a D1Q5 in 1 dimension, Q27 in 2 dimensions, and it goes up to 125 abscissae in 3 dimensions, which is not very efficient anymore. And the question that I had at the beginning of my work was how we can overcome this curse of dimensionality, how it's called in the quadrature literature. And the answer, which I also gave during last year's talk, is yes, we can overcome this curse if the quadrature degree is sufficient, which it has to be 5 or 7 for weakly compressible flows, or degree 9 for fully compressible flows. And the quadrature rule that you apply has to integrate the weight function e to the power minus x squared. And you can test your quadrature rule by the symmetry conditions. So it has to fulfill the symmetry conditions, and then the quadrature rule that you have can be applied. And now if your quadrature rule is not gained by the Gauss product rule, which means by a tensor multiplication, but by abscissae that can be randomly in space, then this is called cubature rules. So these are multidimensional rules which are not constructed by the Gauss product rule for multivariate integration. And there is a vast literature about this field, which is not connected to Lattice Boltzmann, and it's all about the proper numerical integration. Yeah, and by going through the literature, we found a D3Q45 velocity set, which has quadrature degree 9. And this velocity set partially equalizes the larger computational costs of Lattice Boltzmann methods like the SLLBM, but it possibly can also be applied in DAX, for example, which we heard earlier. And this quadrature rule is actually by a paper from 2019 where I found it, called Efficient Cubature Rules by Van Zandt. And he listed it with a number of other quadratures, and this is where I took it and I applied it to my simulations. And these results I will show you during the next slides. And the test case that I looked at was the compressible 3-dimensional Taylor-Green vortex, which was recently published by or proposed by a number of publications at Reynolds numbers 400 and 1600 for Mach numbers up to 2.0. And this is the reference against which I compare the SLLBM for compressible flows. And this test case features shocked flows. So you have these strong shocks in the beginning of the simulation, and then the entanglement of these vortices and ever smaller vortices during the rest of your simulation. So your solver has to be able to deal with both shocked flows and vortices. And if we compare the kinetic energy of the SLLBM against the reference from 2018, we see that we have a very good agreement of the kinetic energy. And we repeated this the simulations with a very naive approach, I have to say, using on-lattice velocity sets, using an on-lattice solver. And we can see that, so for the equilibrium, for example, we used the same fourth order equilibrium, but we used an on-lattice streaming step. And we see that this approach is not able to simulate the high Mach number flows. So for this D3Q103, we see that up to Mach number 1.0, the kinetic energy is quite well matched. But for the higher Mach numbers, we have problems and unstable simulations. And the same applies for another degree 9 velocity set, on lattice velocity set of 3 dimensions with 107 abscissae. So coming back to the SLLBM, we also looked at the solenoidal dissipation at this Reynolds number, and we see that the agreement is quite good, but we can even improve the agreement if we decrease the time step size. So for the smaller time step sizes, we see that the agreement with the reference is better, which indicates that our method acts at large time step sizes like a temporal filter, so that yeah, you can improve this by decreasing your time step size. Comparing to the other publication with Reynolds number 1600, we also see a very good agreement with the Reynolds with the reference, and this reference presented results up to 1.25 in terms of the Mach number, and also the solenoidal dissipation was quite accurate, with a small deviation in the 1.0 case. And we also see a deviation in the 1.25 case if we have a polynomial of the interpolation of 2. But we can improve it by using an interpolation polynomial of order 4, which we use in all our other simulations. So normally we use the higher order interpolation to mitigate mass and momentum losses during the interpolation. So the outlook will be to now consider boundary conditions, and this is a very early test case which I wanted to show to you. A cylinder flow at Mach point 1.5, and we implemented bounce back boundary conditions for this test case. And also we can use body fitted meshes, which is a feature of the semi-Lagrangian method. And we will look at airfoils and other three-dimensional flows in the future. Yeah, this will be part of my next year's talk, I hope. So this concludes my talk. It was about how to find efficient velocity sets for off-lattice Boltzmann methods in the semi-Lagrangian lattice Boltzmann method in particular. And if you desire more information, you can look at our publications. And this concludes my talk at this point. Thank you very much.
Thank you, Dominic. And we have a question, okay, from Benedict.
Hey, Dominic.
Okay.
Hi, Benedict.
Thanks for the nice talk. It's very interesting. So I had just a small question. Have you looked at the stability ranges or temperature ranges that you can achieve with this lattice? So what's the limitations there, or in general Mach numbers?
Well, if you use a Hermite polynomial for your equilibrium, then your temperature is rather a moment of your in your system, right? So we did not encounter that strict temperature ranges or limitations. So we tested it with a test case where we had a temperature range of 1 to 1000, and it worked in a rather easy test case, I have to say. But it seems as if the temperature range is not the problem of this approach.
Okay, thank you.
Okay, another question is what kind of acoustic CFLS can you achieve with this stencil?
So yeah, I never expressed actually the time step size in terms of CFL numbers, because it's always a question of definition. Normally you define your CFL number in terms of your largest velocity, discrete velocity in your stencil, right? And then I would say that you can reach CFL numbers for the Lagrangian vortex, for example, up to 10 or 20. And the other question is?
Is the dissipation induced by the interpolation? Well,
yes, there is definitely a sort of dissipation, but you can decrease the viscosity which is introduced by the dissipation which is introduced by using high order velocity sets. No, high order interpolation polynomials, I'm sorry.
Okay. Okay. And what is the maximum ratio of temperature the stencil can handle?
Yeah, that is what I answered earlier. I tested a test case of 1 to 1,000 and it worked. So it seems not to be that a real problem.
Okay. An interesting question. Are you using for the D3, Q103 and 107 any kind of high order regularization?
No, that is what I meant with this is a rather naive approach. So I used the regular BGK model, which I also used during the entire SLLBM simulations here. So the only thing I changed was really the velocity set and the way of streaming, going from off lattice streaming to on lattice streaming. So I have to say this is why I said this is a naive approach, and it might not be that fair.
Okay, thank you. I think the last question for the quadrature problem, have you considered expressing your integrals in spherical coordinates and getting the quadrature as a product rule between a radial quadrature and an angular one?
So at the moment, I didn't consider it, and to be honestly, I spent not that much time in actually constructing rules, but I more or less used the rules that were already available. But I'm quite sure that there are even better quadrature rules available out there, which are not yet known. So there is a theoretical limit for the quadrature degree 9 of 35 discrete velocities, which eventually can be reached, I think. Yeah, but this might be one approach instead of using your Cartesian grid using spherical coordinates. Yeah.
Yeah, thank you. Okay, thank you, Dominic, for the presentation. I think we can move to the next speaker. And I have to give the permission to the next speaker. Just a moment, please. Okay, probably now you can share the screen.
Yeah, can you hear me?
Try.
Everyone
Okay.
can see my screen?
Okay, we can see your screen. Thank you. Okay, so the next speaker is Isik Yo. And the title of the presentation is Hybrid Recursive Regularized Lattice Boltzmann Model for rotating overset grids. Please, thank you.
Thanks for the introduction. I'm Hishik. I'm a PhD candidate in the M2P2 laboratory in the CNRS. Today I'm going to talk about hybrid recursive regularized LBM model with the rotating overset grid. But I want to apologize that actually my subject is slightly modified from the submitted abstract. So today I won't deal with the compressible model. And this work is done with Dr. Barali, she was postdoc, and Professor Fabier and Professor Sago. So I'm working in the laboratory named M2P2 CNRS. The director is Sago, and we have more than 25 people fully working on LBM in the wide range of working scope from industrial application to the biological application. So in this research, I used a code which is named ProLB, which is MPI supported LBM solver. So in the M2P2 laboratory, we are focusing on developing physical module. And there is a company named CS. They are working on software part and also distribution of the code. And we have several different industrial partners. From them, we can get some feedback. So the motivation of my research is, as you may know, more and more people using lattice Boltzmann method in industrial application, thanks to its cheap cheap computational cost. And one of application is rotating geometry, such as turbo machinery or small scale fan. And especially my interest is how to increase accuracy of LBM or how to increase stability of LBM in simulating rotating geometry. So more specifically, how we simulate the rotating geometry in CFD. So one of the common ways is use two different meshes at the same time, which is called overset mesh, or someone called it a chimera mesh. And since we are using two different meshes at the same time, the interpolation between two meshes are necessary. And also, apart from fixed region, in the rotating region, they use a rotating non-inertial reference axis. Because of that, all the physical values and vectors in the rotating region, we need to consider a fictitious force at each time step. So for example, this is the figure of the 3D rotating cylinder, which I use it by myself. Blue is the fixed mesh, and red is the rotating mesh, and black one is the 3D rotating cylinder. The cylinder is rotating as being attached to the red rotating mesh. And in this, there is an overlap area. In this area, the interpolation between a fixed mesh and the rotating mesh happens. And I think this is one of the classic and the standard method. But as you may, it's quite complicated, so numerical errors are inevitable. So this is brief history about applying overset grid method in LBM. So to my knowledge, the first approach to apply overset mesh in LBM was published in 2011. This is the reference which is introduced in the slide, the one before. And recently, there have been several approaches applying more advanced collision models, such as DLT collision model or cumulant LBM in the overset grid. But up to now, no regularization-based LBM model has been tested yet. So in this research, my proposal is to apply a hybrid recursive regularized collision model to the overset grid method. So for someone who might not familiar with a hybrid recursive regularized collision model, I will explain briefly about what is the HRR model. So for that, first I need to start from BGK. So in the basic BGK model, we define the non-equilibrium part as a difference between distribution function and equilibrium function. And by doing so, we hold full order of the non-equilibrium terms from first order constant number to the infinity. However, in the regularization based model, we filters out redundant high order non-equilibrium terms. So this comes from the idea that we need second or up to third order moment to recover Navier-Stokes equation from LBM. So this is done by, first step is to compute a second order moment, which is done by projecting non-equilibrium part onto the second order Hermite polynomial. And then using this second order moment, we reconstruct the non-equilibrium part from this second order moment. And if one thing, second order moment is not sufficient, we can also calculate a third order moment and then reconstruct the non-equilibrium part by using second and third order moment. And so idea is like, so this reconstructed non-equilibrium value is work like having information related with second and third order moment. And it shows that it gives improved stability. And then what is HRR model? So in the HRR model, we can define the non-equilibrium tensor in two different ways. So first, we can, as I explained in the previous slide, we can just use the second order moment computed from Hermite polynomial as a standard way. But in the meantime, at the same time, we can define the second order moment from the finite difference, because this comes from the fact that the second order moment is related with shear stress. So first we compute the shear stress from the finite difference scheme, and then using that finite difference value, we can compute the second order moment. So in the end, in the HRR method, the second order moment will be linear combination between standard moment and the moment coming from the finite difference scheme. So in this research, if I use the sigma equals 1, it means I just use the moment coming from the standard Hermite polynomial. So this is called recursive regularization. And also, but when the sigma is less than 1, it's going to be a hybrid recursive regularization. For most of part of my research, I use the standard recursive regularization, and I will tell you exactly where I use a hybrid recursive regularization method. So next key point is about fictitious force. As I explained you before, in the rotating region, since we are using non-inertial, since all the vectors and flows are defined with respect to the rotating reference axis, we need to consider fictitious force. We need to consider this fictitious force at each collision and streaming step. And this fictitious force is actualized by using the Gauss forcing scheme. And another key point is interpolation. So since I'm using a two different mesh system in the overset grid, they need to communicate each other. So for example, this is the fixed grid and the black line is the border of the fixed grid. And each node is receiving the information from surrounding rotating node. In case of 2D, we receive the information from 4 surrounding nodes. And in case of 3D, it receives the information from 8 surrounding nodes. And it happens same at the border of the rotating region. So at the border of the rotating mesh, they receive the information from surrounding fixed mesh. So I interpolate the value, macroscopic values such as rho, u, and non-equilibrium tensor. And after the interpolation, I reconstruct the distribution function. And here I consider both a linear interpolation and second order interpolation to see the effect of different order of interpolation. So now I show you some numerical result. Before I show you the numerical result, I will explain how I evaluate the error. So for example, let's say I simulate a very simple uniform flow without any complicated solid geometry. In this case, we can just run the simulation, this uniform flow simulation on the single fixed mesh. However, we can run the same simulation on the overset mesh scheme. So in this case, the uniform flow will transfer to the rotating mesh after the interpolation. And inside the rotating mesh, all the vectors will be transformed to the rotating reference axis. And so in both cases, we'll have same physically same. They are physically same, but their computational features will be different. So by comparing those two, we can analyze the error, which is purely coming from the overset mesh scheme. And then what will be the source of error? So one possible source will be using discrete forcing term, because as I explained before, we have to use discrete forcing term inside the rotating region. So it will give a discretization error, which is apart from the error of the standard LBM. And also inside the rotating region, all the flow vectors are defined after adding the rotation mesh speed. So if the rotation speed is become higher, or the coordinate of the mesh coordinate close approach to the outer region of the rotating mesh, it will have a higher velocity, and it can be another source of error. And of course, since we are using an interpolation, the numerical error coming from the interpolation will be added. So I think in the end, the errors of the overset scheme will sum up all those three factors. So I think it is very difficult to decompose each component, but still I think it will be interesting to see the numerical result as reminding these factors. So this is first test case, a uniform flow. So I run the uniform flow on the overset mesh, and I run the same uniform flow without using overset mesh on the simple mesh, and I subtract those two. And this is the spurious error coming from the BGK. And the right one is the error coming from the HRR model. So here, since I use sigma equals 1, it is a standard recursive regularization model. And it shows that errors are reduced as when I'm using the HRR model. And this is the this graph is quantitative value. So at different forcing term here, forcing term means this is a discrete forcing term to actualize the fictitious force at each collision and streaming time step. And at different forcing term, it shows the HRR model gives less error compared to the BGK. And I run the mesh convergence test in the same, similar uniform flow test case setup. So here I check the error of the force as increasing number of mesh. and it shows a second order discretization error for both when I use HRO and BGK. I think it might support the robustness of the scheme, but at the same time, it shows the HRO gives less spurious error compared to the BGK. And I want to remark one more thing. So here I also check the error of the non-equilibrium tensor. So since this test case is uniform flow, actually non-equilibrium tensors are supposed to be 0 because non-equilibrium tensors are shear stress. But as you can see, there are some values for non-equilibrium tensor, and it means this is error coming from the overset scheme. And I think it is very difficult to derive definite conclusion just by using these two figures, because actually like a full simulation is dynamic process, so non-equilibrium tensor will be affected by the velocity and the velocity will be affected by non-equilibrium tensor. So it is not easy to derive definite answer, but just considering the fact that the difference between HRO and the BGK, relying on how to define the non-equilibrium part. And also another point is like there is another research. Actually, there are many other research which shows the HRR model can suppress the spurious mode in the non-equilibrium part compared to the BGK. So considering all those facts, we might derive the conclusion that with HRR model we can secure more accurate non-equilibrium tensor, and thanks to that we might get a more accurate force or first order moment. And it will give a more accurate overset scheme in the end. So next test case is Poisson flow, and this Poisson flow test case, I want to show you the effect of the interpolation order. So here the interpolation happens at the border. So here outer boundary of the rotating mesh and the inner border of the fixed mesh. And as you can see, when I increase the interpolation order from linear to second order, the error of the velocity field is reduced. And also I studied the error of the spurious noise. Here I define the noise as a fluctuation of pressure. So it shows that the spurious noise generate at the border and propagate through the field. And when I increase the order of interpolation, it suppressed the spurious noise. And actually, amount of improvement is more larger in the spurious noise compared to the velocity when I increase the order of interpolation. And the next test case is vortex, conductive vortex. So this is the rotating vortex which flows over the overset mesh. And so when the rotating vortex penetrates into the rotating mesh, it goes through the interpolation, and then all the vectors are transformed to the reference frame, and also in this area the discrete forcing term should be included. And because of all these process, the initial vortex structure will be dissipated according to the time. So proposes to keep the vortex structure as long as possible. So for example, as a reference, I run the same conductive vortex without using overset mesh, just on the simple single fixed mesh. So here the black line is the density profile from the reference. So proposes to keep to make the density profile as close as possible to the reference. And as you can see, when I run the overset simulation with BGK collision model with bilinear interpolation, there is a significant amount of dissipation. But when I change the collision model from BGK to the HRO, the amount of dissipation is becomes smaller. And when I increase the interpolation from bilinear to second order, the density profile becomes even more closer to the reference. So from this figure, we might conclude that HRR model is superior to BGK in conserving vortex structure, and also second order interpolation gives less dissipation compared to the linear interpolation. And this is the same conductive vortex test case. So in this time, but this time I checked the spurious noise. So here I define the noise as a fluctuation of pressure, and I evaluate the spurious noise. So I ran the same simulation, like the same vortex simulation on the overset scheme, and the same vortex simulation on the single fixed mesh, and I subtract those two pressure fluctuation to evaluate the spurious noise, which is generated from the overset scheme. And as you can see, the noise is generated near the border and flow through the field as following the free stream velocity. But when I reduce the sigma from 1 to 0.995, it shows that it killed some amount of spurious noise. And just for reminding here, the sigma means like how to define the second order tensor. So here in the HRR model, we define the non-equilibrium part, we reconstruct the non-equilibrium part from the second order moment. And to define the second order moment, we can use the standard second order moment computed from Hermite polynomial. But also we can add some amount of some portion of the second order moment, which is computed from finite difference of shear stress. So it works like when we slightly reduce the amount portion of the finite difference part, it works like adding the artificial viscosity. And actually similar observations have been made in different contexts, such as mesh refinement by other researchers. And because in the mesh refinement, we have to also do we also have to do an interpolation between coarse grid and fine grid, and it will give spurious noise from the interpolation, and it shows that slight amount of adding the finite difference part kill the spurious noise. But I think actually exact mechanism is still open question. And this is the PSD curve which quantify the amount of noise. It shows that from sigma equals 1 to 0.995, it approaches to the reference.
2 minutes.
Yes, yeah, thanks. The next test case is a rotating cylinder. This is the low Reynolds number. Reynolds number equals 200. Rotating cylinder in a uniform flow channel. And here I use the recursive regularization model with overset grid. I compare the result with a finite volume-based Navier-Stokes solver. And it shows a good agreement for both lift coefficient and rate coefficient at wide range of rotational ratio. And the last test case is the 3D rotating cylinder with LES. Here I use the recursive regularization model. I use a Smagolinsky LES model. And as a reference, I compare with the finite volume-based Navier-Stokes solver, and with different references, it shows a good agreement in terms of lift and drag coefficient. So this is a conclusion. So I applied the HRR model to the rotating overset grid, and it shows that HRR model enhanced the accuracy of the scheme compared to the basic BGK scheme. And it shows the gross Worthington gives better result than the Hertz Worthington. And I checked the higher order interpolation gives improved result. And also I found the second order tendency, which might support the robustness of the scheme. And also, as compared with the conventional finite volume-based Navier-Stokes solver, it shows good agreement in terms of the lift and drag coefficient. Yeah, thank you. This is end of my slide.
Thank you for the presentation.
Yeah.
And we have several questions. Okay, the first, what is the difference for the hyperviscosity between HRR model and the cumulant LB model? And do you try sigma equal to 0?
I don't know exactly how the cumulant lattice works, so I cannot give an answer about that question. But the other question about sigma equals 0, yes, when I apply the sigma equals 0, it will give much more stable result, but it's very descriptive. Yeah.
Okay, other question, did you try to run transonic supersonic simulations with a rotating object
Not yet. Not yet.
Okay.
No.
So,
So
no
all the
other
results I presented here is in the weakly compressible region without using any entropy or energy creation.
Okay. What was the Reynolds number for the last case?
5,000.
Okay. The fictitious force increases linearly with the radial distance in a rotating frame.
Yes, exactly.
Do you experience numerical issues as the force can grow to be very large?
Yes, exactly. So in the rotating region, the amount of force is linearly increased according to the coordinate. So as it close to the outer boundary, the amount of error is more increased.
Okay. Okay, so thank you again for the presentation. And we can move to the last but not least speaker of this morning. I should give him the permission to share the screen. Okay. Okay, the next speaker is Habbi Manhu Dahuria, okay, from the ATH of Zurich. And the title of the presentation is a fluid structure interaction of rigid bodies in compressible flows. Please go ahead.
Thank you. Hello, everyone. So welcome to my talk on fluid structure interaction of rigid bodies in compressible flows under the group of Professor Carlin at the Department of Mechanical and Process Engineering at ETH Zurich. Right. So a majority of fluid flows of interest that we simulate interact with solids. However, usually we tend to kind of ignore the effect of the fluid on the solid. We tend to focus more on how the solid interacts with the fluid, the effect of the solid on the fluid flow. However, accounting for this interaction is significant for many complex phenomena in order to mimic the real world case. So we have several examples that you can see here. So fields range from as diverse as biofluid mechanics or biomechanics to aerospace engineering, such as this case of a FSI of a parachute at supersonic speeds, which has also been super interesting, a development that's been going on with the Mars rover recently. Right, so as we today focus a lot on compressible flows already, we noticed that Lattice Boltzmann has developed and matured quite a lot for the simulation of compressible flows. However, the focus on fluid structure interaction using these has not been too much, I think, in literature. So not a lot of work has been done in literature, especially in LB. So here we're presenting our LB coupled fluid structure interaction model for rigid bodies, and we present several low and high speed test cases to show how our model works. So quickly covering the background LB model, we have a two population LB model. So with one population for conserving the mass and the momentum, and the other population for conserving the energy. And we have a D2Q9 lattice. As we all know, it's been reported in literature many times, if we couple these two things together and try to solve compressible flows with it, we have these spurious terms that emerge in the higher order moments, and then we can't really go that far, and we can't really have fully compressible flows. To solve that problem, we introduce correction terms. So this is an approach that's quite commonly taken in literature, and we follow the same approach. We have these correction terms, and using that, these correction terms that we have, we're able to extend the applicability of our model to moderately supersonic flow. So that's close to, I think, 1.5 Mach number is what we're able to achieve. Another thing that we do here is, since we're using, we have fluid structure interactions, so we will have moving bodies. So we use the ALE, the arbitrary Lagrangian Eulerian description of the Boltzmann equation, which allows for deformation in the domain. So the equation is there on the top left, right here. So the form of the equation is quite similar to the regular LB form. The only difference you will notice is the CI hat, which is essentially a transformed lattice velocity that we use. So if you look at the figure on top of the equation, we essentially have all our simulations that are done on this undeformed domain, and we need a mapping. So we need this mapping G of X that goes from the deformed domain to the undeformed domain. And once we have this mapping, we can get these transformed lattice velocities Ci hat. Obviously, a drawback of that is that the lattice velocities are no longer on lattice, so we don't have integers anymore. And so we need some sort of propagation scheme, an off-lattice propagation scheme. And here we use the semi-Lagrangian propagation with ALE to get around that problem. So ALE, essentially, we use it because it allows us for large deformations to take place. And it kind of uncouples the fluid velocity from the mesh velocity, and then it allows us to deform the mesh as we so please. So like I said, for this we use the semi-Lagrangian propagation, in which we essentially reconstruct the population at a departure point using a finite element reconstruction. In our case, we use a second order finite element reconstruction. The collision terms remain unchanged and local, so there's no difference there. And like I mentioned, all the computations are performed on a reference domain. Another advantage here is that we're now able to, since we're already off lattice, we can use unstructured meshes, which are quite important if we're dealing with complex bodies and high Reynolds number flows, especially wall-bounded flows. And especially here, now that we have FSI and the effect of the wall is quite significant. In all the cases that we present here, we use a second order finite element mesh, such as the one presented here, which is used later in one of the simulations. And yeah. So now if we're using a finite semi-Lagrangian approach or an off-lattice approach, which leads to conforming meshes, of course, we need to ensure that that mesh conformity remains. It's not like a standard lattice where the underlying lattice does not change. So we need a methodology to be able to keep this mesh conforming at all times with the body. And so that the mesh doesn't degenerate as well. So we need to keep this mesh quality in the boundary layer region, specifically if we're dealing with, again, fluid structure interactions. It is also prudent to kind of localize these mesh deformations and not have mesh deformations in the whole domain, because if you want to deal with multiple bodies, then that is also important. And that is something also we will cover later. So the methodology that we use here is the approach of blending functions. So we essentially solve an algebraic equation. Here we have a fifth order algebraic equation. There are others that exist. It's not a unique equation. And this allows us essentially to keep the mesh deformation local to the body. The basic process is, if you look at the figure on the bottom right, we have a small region around our body that is the so-called rigid region, which is where the mesh moves exactly with the body. So the motion of the mesh is exactly the same as the motion of the body. And away from that region, we gradually start to decrease the mesh deformation so that after a certain point in the domain, the mesh is completely stationary. There's an animation here that can show you how this works. Essentially, so we have an aerofoil that's plunging. On the left, we have what would happen if we had a rigid deformation. So the whole mesh is essentially moving together. And on the right, you can see the result of this blending function approach that leads to, this localization of mesh deformation. There are other approaches, of course. So there's a usual approach to deal with this is the solution of PDEs. So you usually solve something like a linear elasticity equation, which is a PDE, to be able to get mesh deformation. However, that's obviously very expensive. And we don't do that here because we find that for a lot of test cases, that is a bit overkill, although it is necessary for certain cases. Again, so using this approach, we don't have to remesh. So again, since we're doing body conforming mesh, remeshing is extremely expensive and we don't want to go there. So this approach also allows us to get around that. And for all the test cases that we present here, this approach is sufficiently robust and does not lead to any spurious noise in the solution. Right. So quickly over the boundary conditions. So we use here a partition solver which is with using a staggered coupling. So what that essentially means is that our LB solver and our structural solver, which here is an ODE solver using RK4, are solved consecutively, one after the other, sequentially, one after the other. So we have a fluid time step, which passes on the force experienced by the body to the structural solver. The structural solver calculates the displacement and passes it back, deforms the mesh, and so on and so forth. The stability of such a system, in our case, is again limited by the CFL conditions. The RK4 solver is quite stable, the ODE solver, and we're only limited by the fluid time step. Another problem that usually arises due to this nature of this first order coupling, which is the partitioned staggered coupling, is this added mass effect. However, for compressible flows, it's been noticed in literature that it's directly proportional to the time step that is used. And in our case, we experience no such problems. So that's something that we have also found that it's not a problem for us. For the wall boundary conditions, we use grad boundary conditions, where we only replace the populations that are missing at the wall. Now I can show you some test cases with this approach. And of course, one of the bigger advantages of using this first order coupling is that it's very computationally efficient compared to a monolithic solver where you need to do or something that uses sub-iterations to converge at the walls, which is obviously very expensive. So first we have a case of a single cylinder oscillating in transverse flow. So it's an elastic cylinder that's mounted on a spring. It's a simple test case, but it allows us to reproduce the dynamic response quite efficiently, and then we can see very easily how our model agrees very well with literature. So in such simulations of vortex or flow-induced vibrations, a common phenomenon that shows up is this phenomenon of lock-in. So this is essentially where the frequency of the vortex shedding of the cylinder or the body, it sinks or attaches itself to this frequency of the natural frequency of the spring in mass system. And when this happens, you see a sudden jump in the amplitude of the oscillation as well as the lift coefficient. So if you look at the rightmost figure, you can see this happening between Reynolds number 80 and 90, where the frequency, and on the top, you have the non-dimensional frequency of the vortex shedding, and the black line is the natural frequency of the spring in mass system. And you see that around after 80 or 90, this Reynolds number, the vortex shedding frequency starts to attach itself to the natural frequency of the system. And then this corresponds to a sudden jump in the oscillation amplitude, as well as the lift coefficient. So again, we are able to reproduce these phenomena that are quite well reported in literature with our model. Next, we essentially add another body to the system to be so we have two bodies. So now we have two cylinders that are oscillating. However, in this case, we have the two cylinders that are connected to each other via a solid link. And we're able to see a lot of the complex phenomenon using this. We vary both the spring stiffness in this case and the distance between the two bodies. So what is again seen that below a certain distance, so distance between the two bodies, we can see that there's some interference, which is reported in literature as proximity interference because of the two bodies being too close to each other. They only shed a single vortex essentially. So you see in the bottom case. Whereas once the distance increases beyond a certain value, both bodies kind of behave as independent bodies and both shed their vortices independently, which also leads to a higher oscillation amplitude. The interesting cases usually happen, for example, with the case on the bottom, where the distance between the two bodies is twice as much as the distance of the diameter, and the frequency of vortex shedding is it's close to, but not exactly the frequency of the stationary lock-in. And you see in that case, this behavior of beats, the beating vibrations that happen in the body due to the transient nature of the flow between the gap, essentially. We're also like, if you look at the full work that we're about to publish, you'll see that there's a lot of other complex phenomena that are also we're able to reproduce with our model. Now we have two oscillating cylinders, but now they're independently mounted on a spring. And here the distance between the two bodies is kept the same. The only thing that is varied is this reduced velocity, which in turn essentially affects the spring stiffness. So here you see sort of the inversion of oscillation behavior. So for values of high stiffness, so when the spring is super stiff, you see that the upstream cylinder is the one that kind of leads the oscillations. It has high vibrations, and it sort of locks in to the natural frequency of the cylinder, and it kind of causes the downstream cylinder to be sitting between the vortex treats, thereby experiencing lower values of lift coefficient and lower vibrations. However, if we decrease the value of the spring constant or the stiffness, both the cylinders, so this is around the value of VR equals 5 or 6, both the cylinders start to lock in, and at that point, and beyond that point, it's the downstream cylinder that oscillates a lot more than the upstream cylinder, and the upstream cylinder essentially stops vibrating more or less when you compare it to the downstream cylinder. So here's a demonstration of the mesh deformation using these two cylinders that happen. So we have two cylinders, and using the blended mesh, both of them have their own regions of oscillation and deformation. And this is just a demonstration of the blending mesh concept that we use. Finally, we have a transonic airfoil in 2 degrees of freedom. So this is to study a very significant phenomenon in aeroacoustics called flutter. So flutter happens essentially due to a coupling between aerodynamic, elastic, and inertial forces, and is primarily seen on slender bodies. So you'll see it on airfoils, airplanes, rockets, etc., due to the high Mach flows and shockwave interaction with a body that is not completely stiff. So here we have an airfoil that is mounted on a 2 degree of freedom spring. So essentially, you have transverse and like a torsional spring and a regular transverse spring. And the idea here is to capture the 3 major oscillation regimes that are seen in such a case. So what can happen essentially is that the oscillations usually damp out, which is a good case. The oscillations can maintain a steady value and oscillate stably without causing any problems. And the most destructive case, which is usually the interest of a lot of studies, is this divergent case where oscillations diverge, which is called flutter. So here we study the effect of Reynolds number on flutter. We have a free stream Mach number of 0.85, which, as you can see, accelerates with the flow goes supercritical, and you have a shock sitting in the airfoil, which causes the airfoil to start oscillating. And we're able to model this dependence of oscillation behavior on Reynolds number quite nicely. And we're able to demonstrate all 3 regimes. The Reynolds number here are relatively low, ranging from 10 to 15,000, compared to what would be a real life case, which would probably be slightly higher than this. But that's because the model that we use here is a 2D model, and then we can't really go higher than that and expect the results to be correct. But we, like I said, we see all the 3 regimes that are expected to see. And yeah, so in the future work, we intend to basically extend this model to 3 dimensions, so we can test our transonic flutter simulations at representative Reynolds numbers. And besides that, so in conclusion, we presented our Lattice Boltzmann FSI scheme on unstructured meshes for compressible flows. The mesh deformation was handled by a very efficient and quick and fast blending function approach, going away from a PDE solution. And then we validated the model for a variety of rigidly moving bodies. And we were able to accurately reproduce dynamic phenomenon that has been reproduced in literature. Thank you for your attention.
Thank you very much for the presentation. Good work. I don't know if there are questions from the audience. If not, I have a curiosity.
Sure.
Have you considered the momenta exchange between the fluid and the cylinders, they are accounted.
Let me just
Here, yes,
yeah.
exactly.
So could you repeat your question for once, please?
In this simulation, you are also modeling the exchange of momentum among solid and fluid.
Yes.
Okay. Okay. And okay. Second question is that you have in plan also to consider the non-rigid bodies.
Yes, so that's again one of the future works that we want to consider, where we have non-rigid bodies or fully coupled FSI. So in that case, we go forward from an ODE to a sort of linear elasticity PDE, and that's also yes. So that's also one of the future works.
You have in plan. Okay, yes. Interesting. Thanks. Okay, thank you again. And for this morning in the Sala Leone, we have finished. I want just to remind you that the conference will continue. Now we have the lunch break, but we will restart at the 3 p.m. Again in the split mode. So in the Leone room here, we will have the technical session 5. The topic will be bubbles and droplets, while in the room Palma, we will have the technical session 6 about the complex flows. So I want to thank again all the speakers of this morning, and I have a nice lunch to everyone, and we will see at the 3 p.m. again here. Thank you very much. See you later.